Okay, so the last topic I want to cover is reversibility in electrochemical cells. And so we'll talk about having the same reaction proceed in 4 different ways. So let's consider the reaction where we have zinc, which is a solid, plus silver in solution going to zinc in solution plus silver as deposited out as a solid. So there are a number of different ways we could imagine doing this. So one will be, let's just take a container, take some zinc, stick it in a solution of AgNO3, silver nitrate. And what's going to happen? Well, this reaction will start to proceed spontaneously, and the silver will deposit out on the surface of the zinc. So silver spontaneously deposits on zinc. Okay. And a bunch of zinc 2 plus ions are formed. So we have basically solid zinc going to zinc aqueous 2 plus 2 electrons, and then we have silver ions Ag2 plus, which are aqueous, plus the 2 electrons going to 2 silver atoms, which are depositing off as solid. Okay. So if we think about analyzing that, so right after 1 millimolar of zinc is dissolved, right, we have a change in energy of the system, which is Q plus W of minus 364 joules. Okay, so it's a spontaneous exothermic reaction. There's no work done, obviously. We haven't even hooked it up to anything. And so, so all of it is going to heat, right? So Q is equal to minus 364 joules, releases 364 joules of heat. Okay. So let's say we were to do this slightly differently. This time we actually create a galvanic cell. So we have a zinc electrode, we have a silver electrode, and we have a wire going between them that we can open and close, and we put an ammeter on it. Okay. And we have our electrolyte, and we maybe put a semi-permeable membrane between it. So here we have 1 mole of AgNO3. Here we have 1 mole of ZnNO3 2. Okay. And when we close the switch, a reaction starts to happen. So at the anode, we have the reaction that the solid zinc goes to Zn2 plus aqueous plus 2 electrons. Right at the cathode, we have the 2 silver ions combining with the 2 electrons and becoming silver. That'll deposit out on the silver electrode. And so overall, we have the master reaction, right? Zn plus 2Ag 2 plus aqueous, going to Zn 2 plus 2Ag solid, right? These are aqueous. Okay. So what happens when we analyze this case, right? So in this case, the current flow is determined by the resistance due to the leads and the solution and the contacts, right? So we can ask, what is the equilibrium voltage for silver ions in equilibrium with silver? And we would get 0.8 volts. What is the equilibrium voltage of the zinc in equilibrium with the zinc? We would get minus 0.76 volts. So we get a total delta V of 1.56 volts. Okay. So if we assume a resistance in the circuit of 2 ohms, right, then we close the switch for 250 seconds. Then we can calculate a current, that's just delta V over R, which would be 0.78 amps. And from that we can get how much charge has transferred. That would be 0.78 amps times 250 seconds, so that would be 195 coulombs of charge. So the number of electrons transferred would just be that divided by the coulomb per electron, which we get something like 2 times 10 to the minus 3 moles of electrons. Okay. So how much useful work is done in this case? Well, 0, right? We haven't actually hooked anything up to the circuit. We're just running it through our wire. And how much dissipated heat? Well, the work done going through the circuit, so let's call that WQ, is minus I squared R times T, so that's going to be 304 joules. And so the total change in energy of the system is equal to the heat plus the electrical work done plus the work dissipated in the circuit. So this is the exothermic heat of the reaction. So we have Q minus 304 joules is equal to U, and we know that has to be 300 minus 364 joules. So Q, the exothermic heat due to the reaction, is just minus 60 joules in this case. Right. So we're dissipating most of our energy by sending electrons through the circuit, the 304 joules, and dissipating much less just due to the reaction. Okay. Now let's take case 3. Case 3 will be when we actually use the circuit to do some work. So now we're going to take the same electrochemical cell, so zinc, silver, but now, and we're going to have the semi-permeable membrane and our same 2 electrolytes. But now we're going to hook this up to some kind of load. We're going to actually hook it up to a motor or something. Okay, so this is our load, and we're going to say that's an 18 ohm load, right? So the circuit is 2 ohms and the load is 18 ohms. So in that case, the total resistance is going to be 20 ohms, right? And the current is going to be delta V over the total resistance. So the current is going to be 1.56 volts over 20 ohms. So we're going to have 0.078 amps in this circuit. So now the current is going down, right? The current has gone down by a factor of 10. So in order to transfer a similar amount of electrons, we're going to assume a a time, so we still want Q to be 195 coulombs like we did here, so we're going to say the time is 2500 seconds. Okay, so the useful work done now is not 0 like it was before. It's going to be equal to I minus I squared R load times time, so minus 0.078 amps squared times 18 ohms times 2500 seconds. That gives us minus 274 joules. The work dissipated as heat by electrons going through the circuit is going to be minus I squared R do the circuit. So we're calling that R, let's call that RQ T. So that's going to give us minus 30 joules again. Or no, this is much less now, right? Because our current has gone down significantly, so the amount we're dissipating in the circuit is much less. And we know that the total delta U, which is Q plus WEL plus WQ, has to equal Q minus 30 joules minus 274 joules. So Q, the amount of heat energy dissipated in the reaction, so Q here is minus 60 joules. Okay. So we can now think of the last limiting case, which is what if the load were infinite number of ohms. In that case, the current would be 0, right? So as a consequence, the energy dissipated in the system would be 0, but the electrical energy would, in that case, be Q times delta V. The voltage wouldn't change, right? So we would get all 300, right? Because this is the ultimately slow case, the reversible case. So we would get 304 joules out in electrical work and minus 60 joules in heat. And again, the change in energy would be 364 joules. So we have a situation where as we increase the load, we're becoming closer and closer to the reversible reaction. And we're getting to the point where we're getting out as much work as we can as the load increases.